So, in the morning we were looking at algorithms, but along the way we kept asking this question, can we do better? Specifically, how do I show that it cannot do better, right? That so we looked at the algorithm to find max and min, and in fact second max. We saw some algorithms, and I mentioned this notion of also guess my number. For these problems, either I actually proved or gave some hand waving argument to show that some good algorithm we came up with is the best in terms of at least on the number of comparisons in that model, right. So, here for example, n minus 1, here it was 3n by 2 minus 2, and here it is n plus log n minus 2, and here it was log n. So, these are bounds which are fairly tight in the sense that one can show using some adversary argument that any algorithm, for every algorithm there exists an input on which the algorithm will take at least this many comparisons. That's the kind of argument. Okay. So, let me so I can add more problems which you can show by adversary. Maybe I will set up a problem sheet and mail it to you for you to try. So, now I want to get into a different argument to show lower bounds. So, we will start with sorting. Okay. Again, some of you have seen this proof, but for the benefit of those who have not, let me go over it again. So, what is the sorting problem? You have a list of n numbers and you want to arrange it in either increasing order or decreasing order. Okay. So, one can keep finding max. For example, I find the max, put it in the last position, and then find the next max, put it in the next position, and so on and so forth. That would be one such algorithm, one algorithm which actually organizes the entire list in sorted order. How much time will that take? N square. Everyone see that? Do you see this? Yes, no? Okay, why n square? No. Okay, so you don't see it, right? So, what is the algorithm? You are finding the max, right? You are finding the maximum. How do you find the maximum? Using the morning algorithm we saw for maximum, right? Create some variable, run through the loop, and then put it in the last location, right? Exchange it with whatever, wherever the max was. Then on the remaining, find the max again, same algorithm, put it in the next last location. Keep doing it. It is one sorting algorithm. And how many comparisons will it take? Can you give a exact count? N minus 1 for the first step plus n minus 2 plus, by the way, I have heard so many times when I ask this question, people say n factorial. Okay. You know why n factorial? Because they think it's n minus 1 into n minus 2 into n. So, it is n minus 1 plus n minus 2 into n minus 3 all the way to 1. If you add that, that is n square. Okay. That is one such sorting algorithm, but sorting is a very well known important problem, and in the algorithms course there are a number of sorting algorithms you learn about. And there are, so this is not necessarily the best algorithm, there are algorithms that can improve this to n times log n. Okay. So, big O of n log n, there is merge sort, there is heap sort, and so on. Okay. Now, so now what is our generic question we want to ask? Can we do better, right? That is our question for every algorithm we are going to come up with. So, can we do better than n log n, or in other words, how do we argue that n log n is the best for every sorting algorithm? Okay, so somebody who knows the proof, you said you know the decision tree proof. Can you give a high level idea of it?
Online I read it sometimes, so I'm not remembering.
Okay.
So,
Okay.
start with the original sequence.
Mm-hmm.
Then
Anybody else? Who,
There are n factorial comparisons in any level in the decision tree.
in factorial.
Comparisons.
I know. Sorry, so he captured the n factorial. Okay. So now let's do it this way. Suppose I give you 4 elements to sort. Okay. So let's say A, B, C, D. Okay. Can somebody give me a sorting algorithm to sort these 4 elements? Right? Any sorting algorithm. What would you do? Let's call these 4 numbers A, B, C, D. All you are allowed to do is to make comparisons, and let's even assume, for the sake of simplicity, that all these elements are distinct, no duplicates. How do you sort? You want to write a sorting out. Which elements? Okay, let's even make life simple. There are only 3 elements. Give me a sorting out. Okay, let's start, right? So if A is less than B, then else, yeah. So what are you going to do? If A is less than B, then what are you going to do? So you are going to compare A and B. If A is less than B, then
B is less than
then compare B and C.
compare B and C. Okay. Then if B is less than C, then output A less than B less than C. Okay. In this case, if not, what do you do? So what do we know? A is less than B, but B is greater than C. Compare A and C, right? So if A is less than C, then what is the answer?
AC.
B is
Yeah, AC. Because we are in the else case, so that means B is greater than C, which is greater than A. So then you got it. Else, so A is not less than C, then CAB. I am just writing down whatever you just said. I hope it's correct. Okay. Now let's. So this is the case when A is less than B, right? Else A is greater than B, something like that, right? You go on. Any sorting algorithm is going to look like this, right? Except maybe when we start off, we don't compare A and B, we would have compared A and C, whatever, right? But the point is that any comparison based sorting algorithm is going to look exactly like this. We take some pair of elements, compare, depending on the outcome, pick another pair of elements, compare, and keep doing it until you are sure you got the entire sorted order. Correct? So, let us model this whole thing as a tree, right. So, you can model any sorting algorithm. So, I have just said this algorithm, but I am also telling you that any sorting algorithm will look like this. So, any sorting algorithm can be modeled like a tree, where I would say I would compare A and B first. If A is less than B, greater than B, I do something else. I compare some other comparison. If it's less than, greater than, I do, and so on and so forth, right. So, any sorting algorithm, comparison based algorithm, is going to look like a tree like this, because all you are allowed, I keep saying comparison based sorting algorithm. What, can you tell me an algorithm which is not comparison based?
Counting chart.
Counting sort, right. So, suppose you look at a number and say, okay, is it 5, then I put it here. If it's 27, I put, if I know something more about the input, suppose I tell you that the numbers are in some fixed range, and there are various other situations where you can do other things. But this is sort of a general purpose sorting algorithm, models comparison based sorting algorithms. So, any sorting algorithm is like a tree. This is what we call a decision tree, right? In fact, heap sort, merge sort, whatever you think of, they are all going to be modeled like this. Okay. Now, let us understand about this tree. How many, I mean, what are the nodes of the tree correspond to? Comparisons. They are comparisons. Okay. Good. What are the leaves?
All permutations.
Permutations. The leaves give you an output like this, right? So, leaves are the final sorted order. Okay. So, I do not know how the input is. I mean, so that means that every permutation should appear in a leaf, because that means otherwise if your input is at that kind of a permutation, then you are not actually sorting correctly. Okay. So, the number of leaves is what?
N factorial.
How many permutations of n are there? N factorial. Okay. Discrete math question. Okay. So, number of leaves is equal to number of permutations of 1 to n, which is n factorial. Okay. So again, I want to keep emphasizing the fact that this is any sorting algorithm. You come up with the sorting algorithm, call it merge sort, heap sort, your own sorting algorithm. If you're just doing comparisons, this is how it will look like. I model it, I look at what is the first comparison you do, I put it here, and depending on that, you're going to sometimes maybe ignoring the outcome of this, you might make some comparison. That's okay. So that means in both cases, it may be the same comparison, and so on and so forth. So there are n factorial leaves, and we are interested in the worst case time for the algorithm, right? And what does that correspond to in this tree? Height of the tree. Okay. So now it's a binary tree, because we assume there are no equal elements and you have less than greater than. So you have a binary tree. So now I'm going to write a claim, which is that any binary tree with k leaves has height at least
Log K.
log k. Okay, you need to prove this. This is something that you need to prove it. Okay, it can be much more, because your if your tree looks like this is also a binary tree. If there are k leaves, what is this height in this kind of a tree? K or k by 2 or something like that. So it can be as bad as k, but all I am saying is at least, okay, at least log k. Okay, log k would be the nice bushy tree which has that many leaves, but if the tree is very skewed and so on, there can be many leaves. Okay, so that's it. So now, so that means our sorting algorithm, which is modeled as a decision tree, has at least n factorial, as exactly n factorial leaves, and so the number of the worst case time would be at least log of n factorial, and log of n factorial turns out to be omega n log n. Okay. So, that is a proof that any sorting algorithm must make at least log n factorial comparisons. Another way to think about it is there are somehow n factorial permutations it needs to distinguish any algorithm, and by making one comparison it is only distinguishing some half the number of permutations. Okay, and so it needs to do log of the number of permutations. Okay. So, this is sometimes called information theory argument or decision tree argument to show lower bounds. Okay, morning we saw this adversary argument. Here this is a decision tree kind of an argument, and this can be used to show some problems like merging, various other problems. You can show lower bounds. Okay, so at least asymptotically. So by the way, so yeah, omega I did not define it. Okay, thank you. Maybe anybody wants to define? You know what omega is?
The first one is greater than or equal to constant in G of t.
Exactly. So it's sort of like the big O in inverted. So, so in fact, whenever we talk about lower bounds, it must be omega. Okay, good. Yeah, so I'll set up some questions. You can try your hands on trying to use adversary arguments or decision tree argument. So decision tree, again, on comparison based thing, you look at the number of leaves. You figure out, okay, let me throw in another problem. Yeah, let's talk about merging. Okay, so you have two sorted lists. One of size m and another of size n. Each one is already sorted. Okay, and I want to merge these two into one big sorted list. Clear? How do you do it and how many comparisons does it take? Yeah. So, m plus n minus 1, more precise. This part is very silent. We know how to do this merging problem. So, we have two lists which are already sorted in increasing order. So, I want to put them okay. So, I have, in fact, this is the basis for the merge sort problem, merge sort algorithm. So, how do you put both of these arrays together and create one big sorted list? So, how do you do this merging?
Say compare the first elements of the array.
Yeah.
Then put the meaning into the URI.
Right.
Then increment the least elements arrays index.
Yeah. So, you compare these first two elements, first element of A and first element of B, output it whichever is smaller, and then if this is smaller, you move this pointer next and then compare again these two elements, whichever is smaller, output, and you keep going. And this has the number of comparisons is m plus n minus 1. Okay. Now, I wanted to think about in the decision tree model, if you want to merge m element list into n element list, you make comparisons and finally you get a final output. How many leaves will there be? Because ultimately, if you want to show a lower bound using decision trees, all we care about how many leaves. Then it's log of the number of leaves is a lower bound. So, how many leaves will there be? So, you have a sorted list of size m and sorted list of size n. You want finally at the end of this whole algorithm, you get everything merged nicely. Okay, how many possible? I mean, first of all, why is it not m plus n factorial like what you have there? Right, there are n elements. When you are sorting, we got n factorial. Is it possible that it's actually m plus n factorial? All permutations are possible. So, yeah, exactly. So, I cannot have this coming before this in the final sorted order, right? Because each one is sorted. So, use that fact. How many permutations are possible? Okay, that's a question. I'll leave it to you to think about it, and that will eventually give you a lower bound for merging, and then compare it with this upper bound m plus n minus 1. Right? It turns out this algorithm is optimal when m equal to n. You can come up with an adversary argument to show 2n minus 1 comparisons are necessary if m equal to n. But if m is not equal to n, if they are far apart, this is not the best algorithm, at least in the comparison model, to merge these two. Okay. Just to see it, Suppose this list has n elements and this list has 2 elements. How would you merge? If I care only about comparisons, I am merging a 2 element list with an n element list, each is sorted. How many comparisons do I need? Let me make it simple. Yeah. Okay, so let's say I have 5 elements here and I have n elements here. Okay. If I use this algorithm, how many comparisons will it be? 5 plus n minus 1, so that will be like n plus 4. Can you do better? 5 comparisons are in where? How? I mean, I don't know where these guys fit in here. So I have this. Okay, let's say 4 elements. That's all I had space for. And then I have another huge sorted list of size n. I want to merge these two. Can you give me an algorithm which is better than n plus 4? You all know it. Huh? I mean, this algorithm will take n plus 5 minus 1, so that's n plus 4. Okay. How many comparisons? N minus 1 half. Okay, let me make life simpler. Suppose I have 1 element. Why n comparison? This is sorted. I just want to figure out where this fits in. So just do one binary search. This is sorted. Take this element and do a binary search. It tells you exactly where you should fit it in, put it in. How many comparisons? So if I have 5 elements, 5 log n, much better than n plus 4. So this is not. So what have I shown? This is not the best algorithm if n, m is small and n is large. Okay. But it turns out this is the best algorithm when m and n are same. There you can use some adversary argument, but when you do a decision tree lower bound, count the number of leaves. That's a very interesting combinatorial question, that how many leaves will there be if you have m elements here, n elements here, each sorted in that merged list. How many permutations are legal? Then log of that would be the lower bound. Okay. So the point is that you can use adversary, you can use decision tree, whatever fits in, and show lower bounds. Okay. Okay. So I will stop that aspect of that lower bounds for now. Let's move on. Again, our theme is going to be constantly, can you do better? Okay. So let's get on to the matrix multiplication problem. Okay. This is something everybody should wake up, because you are all mathematicians, you have all seen it, how to multiply 2 matrices. So how much time does it take to multiply 2 matrices by the standard high school algorithm you have seen? So let's say A is an n by n matrix, B is an n by n matrix, and I want to multiply and get the matrix C. Okay. Can somebody here tell me what is Cij? Not perfect. Multiply. This is my C. I just want to multiply these two. Cij. Yes, I want somebody here to answer. I'm choosing a question where you should be able to answer, right? Cij is the product matrix. How do I get this entry, right? I throw jth column. What should I do to get this? I asked people at the back. You know. Okay. How do I get ith row, jth column entry of the product?
Summation.
ith row of A multiplied with jth column of B.
B. Exactly, right? So I take the ith row of I and jth column of B. I take this entry and this entry, multiply this entry, multiply, and so on. So in particular, so can you say it mathematically?
Summation.
Summation
AIJ.
Aik
BKJ.
Bkj, the k ranges from 1 to n. This is the product matrix as you would have learnt in high school. Okay, everybody with me? Let's understand how much time, because we care about algorithms. This is an algorithm. How much time does it take? Why n cubed? Again, I want to hear from you.
Each element wants to find the element, means we want to do it for n square times.
Exactly.
So n elements, so n into n square.
Not n element. So each entry, how much time does it take to compute one Cij? It takes n multiplications. So each entry takes n multiplications, and there are n square entries here. So n square into n cubed multiplications. Okay, everybody should be able to say, understand, and say this at the end, right? So you have the standard matrix multiplication algorithm takes n cube time. All right. So now let's ask the question: can we do better? Right? Yes. So this is a interesting question. You have an n cubed algorithm. Can we do better? In 1969, a researcher named Strassen came up, stunned the world by giving an algorithm which takes n power 2.81. Okay. So more precisely, it's log 7 to the base 2. And this is something which is taught in a first year algorithms course. Okay. If you have not seen it, please go look at it, because conceptually it's very simple. It uses this powerful divide and conquer technique. Okay. It uses the fact that two 2 by 2 matrices, which would take normally how many multiplications to multiply? If I give you two 2 by 2 matrices, a 2 by 2 matrix, one 2 by 2 matrix, another 2 by 2 matrix, your normal multiplication algorithm will take 8 multiplications, but Strassen managed to do it with 7 multiplications. Okay. This is some trick he managed to do. All you have to do is look at two 2 by 2 matrices, A, B, C, D, E, F, G, H. If you apply this algorithm, it will take you, there are 4 entries in the product and each one will take 2. So, there are 8 multiplications. He managed to do with 7 with some additions, multiplications, subtractions, and so on. That is all he did. That is all you need to know. You just need to go understand, or in fact, you do not, nobody remembers this. So, you do not even go and look at and remember this. But the fact that he managed to do 8, improve from 8 to 7, and that it can be applied on a recursive fashion on a divide and conquer algorithm to multiply two n by n matrices. You look at the n by n matrix is a 2 by 2 matrix, where each entry is an n by 2 by n by 2 matrix, and then use Strassen's algorithm, apply recursively, use some interesting theorems on recurrence relations, and you come back to improving this. Okay. Of course, we have this question: can you do better? Right? Why is this the best? Is there a lower bound? So it turns out there have been a series of improvements all the way. Now current best stands at some n power 2.236 or something like that. That's the best known. And so the question is not yet resolved. What is the best complexity? Can you do better? That question remains still open, okay, for matrix multiplication. But let us ask the question, how about computing the inverse of a matrix, right? assuming inverse exists, right? So, assuming A is non-singular, I want to compute A inverse algorithmically. How much time it takes is what we want to understand. And do we believe that computing inverse is harder than computing the product of two matrices? Yes, because intuitively it looks like, at least the algorithms we learnt in high school, computing inverse was like, oh, determinant, cofactor, adjoint, you subtract, do all that, whereas matrix multiplication seemed simple enough. But how do I mathematically argue? So let's now I'm going to talk about the third word in that title, reductions, which is, I mean, I don't know how fast I can do matrix multiplication. It's still open. I don't know how to compute inverse, but how can I argue somehow that computing inverse is going to be harder, or at least not easier, than computing product of two two matrices. It looks intuitively so, but that's not a mathematical argument. How do you mathematically argue? Can someone give an idea of, I want to somehow argue that computing product of two matrices is somewhat easier than computing the inverse of a matrix. I mean, complexity wise, if I have some lower bounds or something like that, I can argue, but I don't know. They seem like a hard problem. So I don't know that. And so I can't say, for example, oh, inverse takes at least so much time, whereas multiplication I can do in less time, so it's better. No, I don't know that. So somehow I want to relate these two problems and somehow argue that computing inverse or computing product of two matrices is no harder, or it's easier than computing the inverse of a matrix. Okay. I am not even asking you how to argue, which I will give you. I will give you a proof, but somehow mathematically, how do you think you can say that? Because that's the crux of this notion of reductions, which is going to come from tomorrow onwards in my sessions. So now we are not talking about one problem. That's what we did in the morning. Here is a problem, here is an algorithm, can I show a lower bound? We kept saying this. Now I'm saying, I'm trying to relate two problems, and how do I show that computing inverse? Well, intuitively I know the algorithms I learnt in high school, inverse looks like a harder thing. Those are not mathematical arguments. How would you argue? Any ideas?
Steps followed in an algorithm are a subset of another.
Step followed in one algorithm is a subset of the, okay, nice, okay. So you're saying okay, you're getting into that. So what you're saying is that algorithm for inverse includes, very nice, okay, sort of, okay, intuitively. So algorithms for inverse somehow built into it an algorithm for multiplication. So somehow inverse is harder, okay. So more precisely, what we will show is that, suppose you have an algorithm to compute the inverse of a matrix, okay. I can use that to compute the product of two matrices. That's what I am going to say, right. I don't know how to multiply two matrices, but you are saying I have an algorithm to compute inverse. I will use that algorithm without too much additional cost and find the product of two matrices, right. So, that means if you can solve inverse, I can solve matrices multiplication. That is the argument, okay. So, this is what I am going to say, that a matrix inverse algorithm can be used for computing product of two matrices. It's sort of like what you said. Somehow the inverse algorithm has into it some steps to multiply two matrices. Not quite exactly, but somehow I can use the inverse algorithm to compute the product of two matrices without too much additional overhead. That is the notion of reduction. Okay, I'll make things clear later on, but let's see how this works, right? So what now? Let's understand. So what is the assumption and what am I going to do? What do I want to design? What do we assume? You have an algorithm for matrix inverse. And the reason I am asking this is very important to understand this before we even start thinking about the proof, because later on when we get on to NP completeness and reductions, this direction is important. So we are assuming that there is a black box algorithm. So this algorithm, if you give some matrix A, which is non-singular, I don't want to spend time figuring out whether it's non-singular or not. I'm going to assume that it takes a non-singular matrix. This algorithm, let's call it inverse, will give you A inverse. Okay. How this works and so on, it's none of my business. It's just some black box. Somehow, I'm going to use this algorithm as a black box to compute the product of two matrices. Once I tell you how I'm going to do, it's fairly easy. Okay, nothing magical. It's just fairly simple idea, but the high level idea is important. Okay, so first, okay, so this is given to me a black box algorithm. You give any non-singular matrix, it will give you the inverse. Okay, I'm going to use this to do what? Compute the product of two matrices. So now what is my input? Two matrices which I want to compute the product. So let's assume A and B are the two n by n matrices I want to multiply. I will construct this matrix. I is the identity matrix. So I'm going to construct a 3n by 3n matrix where I is the identity matrix. I'm going to put A here and B here and these are zeros. Then it turns out by magic, by definition of inverse, D inverse turns out to be this. Okay. The fact that this is D inverse is not very hard to verify. You just multiply those two matrices and you see that you get identity. So note that, like the way you said right, in this algorithm, product steps for product algorithm is hidden there. Yeah, it's not quite that, but I have constructed in a way that in the inverse my product matrix is hidden here and I extract it out. That's it. Okay. So it turns out, suppose let's say Mn is the time to multiply two n by n matrices and In is the time to find the inverse of a non-singular n by n matrix. Then what we have shown is that M of n, because I have designed you an algorithm which uses the inverse black box. So, M of n is less than or equal to I of 3n, because I have constructed a 3n by 3n matrix plus some n square, but you know the inverse should at least take n square. So, we can even ignore this, because this is at least n square. Compute the inverse of a matrix of n by n will take. So, M of n. So, I have shown less than, so basically matrix multiplication is no harder than computing the inverse. Okay. So, this is something intuitively we know, because you said inverse is a lot more complicated, but formally we have shown this. Question? No, because it's sort of like less than or equal to. Okay. I will show it's actually equivalent by giving the other direction. That is the more interesting thing. The more interesting thing is that this is more interesting, that inverse is really not much harder, is what we are going to show. Here we have said matrix multiplication is not harder, but I will show the other way and say that no, computing inverse is no harder than multiplication. How do I show that? By the same kind of a logic. What do I assume and what do I have to show? If you have an algorithm which takes two matrices and computes a product, I can use that algorithm as a subroutine to compute the inverse of a matrix. Okay, we will show that in the next slide. Okay, that's surprising that even that's true. Are you with me? Yeah. So matrix multiplication algorithm actually can be used for computing inverse of a non-singular matrix. So turns out I need somehow I need this concept of symmetric positive definite matrix, positive semi definite, okay, that is what it is called, symmetric positive semi definite matrix, and I am actually going to tell you how to compute the inverse of a symmetric positive semi definite matrix, not for general matrix, but then for general matrix I can do some reduction and get that. So, if A is the matrix where I want to find the inverse, I actually compute A transpose A. How do I compute this? How do I compute this? Using matrix multiplication algorithm. Remember, I want to show that it's no harder than compute. So, you have a black box algorithm, because I am going to use that, because I do not want to use an inefficient matrix multiplication algorithm. You have some very clever matrix multiplication algorithm. I will use that to compute B, which is A transpose A. Then you know that B inverse is this. So, B inverse I am going to compute, I am going to tell you how to compute it. I will come up with an algorithm to compute the inverse of a positive semi definite matrix. So, somehow if I assume it is positive semi definite, it is helpful to me, and I am now here telling you it is not a serious restriction, because I can take a general matrix and do this operation and get a symmetric positive definite matrix. So, if I compute B inverse, I pretty much got A inverse, because all I have to do is multiply B inverse by A transpose using your matrix multiplication algorithm, I get my A inverse. Okay. So, I want to get the inverse of A, I will compute the inverse of a positive semi definite matrix. How? I am going to tell you now. Okay. I am coming to that. So, essentially we will focus on inverting symmetric positive semi definite matrices. Okay. Now, here again a magic, right, just like we created a D with some A B and I said D inverse has A B hidden into that, something similar will happen here. So, let A is a symmetric positive definite matrix of dimension n, and let us assume nice things about n power of 2. So, my matrix A looks like this. So, all I am doing is M is an n by 2 by n by 2 matrix, B is an n by 2 by n by 2 matrix, this is B transpose and this is C, because it is symmetric, B transpose and B, this is basically the transpose of that. Then it turns out by some magic A inverse looks like this, okay, some messy expression, but you do not have to worry about it, you just verify this by computing A inverse times A, you get identity. Okay. So, it is not as simple as what we did before, where we said if you have an inverse algorithm, I construct a large matrix, compute the inverse, A B was hidden there. No, here I am going to use some divide and conquer, apply your matrix multiplication algorithm several times to get my inverse. So, first step, the matrix, the positive semi definite matrix A, its inverse looks like this, where S is again some function of C M B transpose, and one can verify, I am not going to get into the details, but trying to show something is symmetric, positive definite is symmetric is easy, positive definite you just have to show that X transpose that matrix times X is strictly greater than 0 all the time. Okay. So, here is an intermediate matrix I compute S and compute its inverse S inverse, because that is used here, and then I am using M inverse, and then I am doing various multiplications, that is A inverse. So, our goal is to compute the inverse of A using some jugglery of this each of these matrices is of dimension n by 2 by n by 2, M and B and C. Okay. So, now all I have to do is to compute A inverse, I compute M inverse. How do I compute M inverse? How do I compute M inverse? Recursively. I am trying to devise an inverse algorithm, right. I do use that same algorithm recursively compute M inverse and M is of dimension n by 2. I will analyze the complexity later, and then it turns out S is the matrix where I am doing some matrix multiplication, subtraction, various things, and that is also of dimension n by 2. I compute S inverse. So, I compute M inverse, compute S inverse, do a bunch of multiplications using your multiplication algorithm. You have an efficient multiplication algorithm, I use that. The inverses are computed recursively and then I compute this multiplication. Okay. So, A is a symmetric positive semi definite matrix. I break it up like this, compute S inverse, and then it turns out A inverse looks like this. Now, let us understand how much time does it take. So, how much time does it take to compute A inverse? Okay. So, let us say inverse n is the time it takes to find the inverse of a non-singular n by n matrix, okay, just a function, and let us assume mm of n is the time it takes for your matrix multiplication algorithm to multiply two n by n matrices. So, now can you tell me a recurrence relation for inverse n? How many inverses are you computing recursively? So, here is one inverse I am computing, M inverse, S inverse. So, 2 exactly. So, 2 and each one of dimension n by 2, okay, plus I am going to put some n square for various subtractions, additions, all that kind of things, right. So, various places has c minus something, there are some additions that are happening, I am just going to say order n square. Now, how many multiplications am I doing? Matrix multiplication. Well, here is one, here is another one, 2, right. B M inverse B transpose, I can actually, okay, some constant number is all I care about. So, 1, 2, 3, 4, 5, 6, 7, 8 if you care. I mean, this is something I could have, it is repeated here. So, I could compute it and store it here. So, it is 1, 2, 3, 4, 5, 6 if you care about, maybe you can. Here, yeah, okay, right. I could have computed this and computed this, then this is the same as this, and then multiply these two. So, some constant number is all I care about. So, I am going to say plus order your matrix multiplication 6, 7, 8, it does not matter, some number. Okay. So, it is a recurrence relation. Now, if you remember your famous master theorem to solve a recurrence relation, yes, okay, good. So, I have two problems of half the size, let us even ignore this, plus some quantity which is greater than or equal to n square. How does this solve this recurrence solution to this? Okay, solution to the master theorem recurrence. If you compare n power log a to the base b, where a and b are this, so that is n, because a and b are 2, 2, so it is 1, and compare this quantity, and this is larger, so this dominates it. Okay. So, this is basically, that is all it is. Okay. I mean, you can also expand it and solve the recurrence relation, it turns out. Okay. So, exactly, I have it here. So, computing inverse is at most some constant times whatever time it takes to compute the product multiplication, and we also saw the other way. So, they are equivalent. Okay. Now, this is nice because we have not shown any lower bound for any single problem, but Now it tells you Strasson's algorithm can be used for computing inverse, right. So, instead of this mn time to multiply two n by n matrices, we know Strasson's algorithm. So, substitute here, then what we are saying is we can compute inverse in the same time using just your matrix multiplication as a black box and using some divide and conquer. Okay. So, the details apart, the message I want to say is somehow relating one problem to another, the complexity. First of all, it is not just about inverse is expected to be harder. No, no. More formally, we can say an algorithm for one can be used as a subroutine maybe several times to solve the other problem. That is exactly what it means by this reduction. Okay. So, that theme is important because it is going to keep coming again when we talk about Turing machines, undecidability, NP hardness, all of this, where you are going to come across this. And number two, that somehow good algorithm for one problem can be used for others. So, inverse, though it looks harder, I can apply Strasson's algorithm, or any improvement anybody has come up with for matrix multiplication algorithm, I can use it to compute inverse of a matrix at the same time, because this tells you that I can compute it in whatever time by using this technique. Okay. Any questions or comments? Okay. So, now we are moving from showing lower bound for one particular problem, that is what we did in the morning, to trying to show some relationship between problems by using one problem as a subroutine to solve some other problem, thereby relating the complexities of these two problems. Okay. I will do one more example quickly in the next 5-10 minutes, and that is to compare again Boolean matrix multiplication and a graph problem called transitive closure. Let us now get into the domain of some graphs. Hopefully, some people will get lightened up. Okay, so Boolean matrix multiplication is very similar. I mean, whatever we have done in matrix multiplication, except our entries are all zeros and ones. Okay, so I have two matrices. The entries are only zeros and ones, and I want to compute the product. So, the product ijth entry is 1. When is it 1? Hmm? No, there is. We are not talking about a graph. We are only talking about two matrices. Here is a matrix A. Here is a matrix B. Let us say it is n by n. It is n by n. And the only thing I am telling you is that this is just some zeros and ones. Now, I want to compute the product, and when is Cij 1? Which both elements? Which two elements? I mean, A is a huge matrix. So,
Some AIK, GAJ is one.
exactly. So, what we did before, we took the ith row and we took the jth column, and we just did multiplied and added to compute our product entry in this normal multiplication. Here we are not doing adding, we are doing a OR, the Boolean OR of this. So, that means, as we said, if some aik and some kj is 1. So, basically what I am, so Cij is earlier it was summation k aik into bkj. So, now it is going to be a Boolean OR over k aik in and bkj. This is 1 and that is 1 should be true for some particular k, then it is 1 and 0 otherwise. Okay. So, this is the Boolean matrix multiplication. Now, all we did for Strasson, whatever, all that will work here, because now when you do all your additions, and the moment this is greater than 1, we know that there is some guy here that gets 1. So, all that works, but people are interested in so called combinatorial algorithm. So, let us see. Okay. So, given the Boolean product is this R, AIK and BKJ. Yeah, I do not want to get it. I mean, I do not think there is a standard definition of what a combinatorial algorithm is. So, something which does not use subtractions, some uses only some logical arguments. One needs to get, wants to get a n power something better than n cubed. This is a famous open problem. Okay. Even to get better, I mean, of course, Strassen algorithm, all these kind of algorithms work, but can you get a pure combinatorial algorithm for some definition of what combinatorial algorithm means is open. It is something people keep looking at it. Let us look at, so again, I am not going to talk about can I improve it, how fast can I do it and so on. I am going to relate to a natural interesting graph problem, and that is this problem of transitive closure of a graph G. Given any graph, I want to construct a directed graph where I j is an edge if there is a path from I to j. Okay. So, in some sense, think of this edge relation as a transitive relation and do a transitive closure of it. So, that is the transitive closure of a, you can talk about it for undirected graph or a directed graph, does not matter, but directed graph is more interesting. So, if this is a 5 vertex directed graph, then the transitive closure, what additional edges will I have in the transitive closure? I will have this edge because there is a path from 1 to 3. Okay. So, transitive closure of a graph means you add additional edges whenever there is a path from this vertex to that vertex. Okay. So, since there is a path from 1 to 3 through 2, I am going to add this edge. What other edge should I add? 1 4 can I add? Yes, right, because there is this path. So, I can add 1 4, 5 2 and 5 3 as well, apart from the additional edges, because those edges are also there, and I can add more these edges.
So initial graph has to be directed.
What happens if it is an undirected graph? Will it always be a complete graph?
It is connected.
It is very nice. Okay. If it is connected, it will be a complete graph. If it is not connected,
Not a complete. Have all
hmm?
all connected components will be complete.
all connected components will be complete. Exactly. Right? Yeah. Good. So, if it is an undirected graph, how do I compute the transitive closure? Find all connected components. How much time does it take? DFS or BFS. Find the connected components. How much time? N plus N. Find all connected components and make each component a complete graph, and that gives you a transitive closure of an undirected graph. Now, we are interested in computing the transitive closure of a directed graph. Directed graph makes it more interesting. Okay. So, how much time does it take to compute the transitive closure of a directed graph? And we are going to relate these two problems, Boolean matrix multiplication and computing the transitive closure. There is a very natural connection, you will see why, how. Questions? Okay. So, yeah, undirected graph, you all came up with a beautiful answer. Okay. So, let us again, right, whenever you are talking about, I am going to relate these problems, it is very important, the direction is important. What is the assumption, what is the problem for which you have the algorithm, using which you are designing an algorithm for the other problem, and how much extra overhead complexity, and that is how you measure it, right. So, here I am going to assume that I have an algorithm which will compute Boolean matrix multiplication, right, using which I want to compute the transitive closure. So, how do you think I can use Boolean? So, somehow matrix multiplication I want to use to compute the transitive closure of a directed graph.
Product of adjacency.
Nice, exactly, true. Product of adjacency matrix with what?
With itself.
Itself, exactly. So, if I take the adjacency matrix for a directed graph, so it will have a 1 whenever there is an edge from I to j. Now, you compute a square. What do you get? Paths of length 2 or even 1 if you had it 1 before, right, and that requires Boolean matrix multiplication. Okay, I mean you can also do whatever Strassen kind of a thing and do it, but Boolean matrix, because whenever in this product you have an ij1, if there is a path of length 1 in aik, akj should be 1, then you have a path of length 2 and you do it. Keep computing a square, a cubed, a power 4, and you can compute the closure. How far can you go? A power n in the worst case. So, that is what you do. Okay. So, it turns out, because you also want to use the fact that you can go from A to A or a vertex to itself. So, you take this is the identity matrix plus A and take it power n, compute ij, where aij is the adjacency matrix of G, and you will get the ijth entry of the transitive closure. Now, let us understand how much time will it take. So, if I assume the product will take m of n time, okay, let us say Boolean matrix multiplication takes some BMF n time. How many multiplications do you need to do? Start with a square, a cubed, a power 4, a power 5, a power 6, how many? N many multiplications looks like. Can I do better? Okay, so n times. So, there is clearly so transitive closure time on an n vertex graph. Can you see this? I hope the screen is not hiding. Is n times bm n time. Okay, so that's one algorithm. Compute a power n and you get it. Can I do better? Okay, in general, let me ask this question. Suppose I want to compute a power n. A is some number, n is some number. Okay, forget matrices, because the same idea will work. I want to compute a power n using multiplications alone. How many can I do faster than n? Right, I can compute a square, a cubed, a power 4, a power 5 up to a power n, that is like n multiplications. Can I do better? How?
So a square and then you a square is a square.
Right.
Is that into itself.
Exactly.
Plus 1.
Right, it is sort of like binary search. So, for example, you compute a power n by 2 recursively and square it. So, it is 1 plus c or n by 2, that is one way to think about it. Other way, in the bottom up fashion, is compute a square and then do a square into a square to get a power 4 directly, skip a cube. Then compute a power 4 into a power 4 and get a power 8 directly, right. So, you can keep doing that, and that will take you only log n many multiplications. Okay. Same thing you can do in the matrices. So, I can, because ultimately for the closure I only care about a power n, right. So, I can do a square and then a square into a square, a power 4. See, a power 4 will give me all paths of length at most 4, it covers 3 also. So, eventually I can do, so that will take order Bm times log n. Okay. And it turns out actually you can make it even order whatever Boolean matrix time. I will come to that in next line. So, this is repeated squaring is this idea, and so that is the computing. So, we are relating time to compute the transitive closure of an n vertex graph with the time to compute the Boolean matrix multiplication. Okay, so, all I am saying is use this log n times and you get this. Let us do the other way. Okay, can be actually I can get rid of this log n, I will tell you in the next slide if I have time, but let us do the other way. So, what is the other way? If you have an algorithm to compute the transitive closure of a directed graph, I can use that to compute the product of two Boolean matrices. Okay. So, I mean the actual idea is simple, but I really want you to again keep in mind the high level thing. What is given and what am I going to do? The high level thing is I have an algorithm this algorithm will take what and what does it give? What is the assumption? Transitive closure. So, what is the input for that transitive closure algorithm? A directed graph, and it would give you TC, right. Using this algorithm, let us call this a TC algorithm. I want to design an algorithm to multiply two Boolean matrices. Okay. As I said, this concept is important because we are going to keep seeing this tomorrow and later. So, now for the algorithm I am designing, what is the input? Two Boolean matrices. I am given two Boolean matrices A and B. I want to multiply them. I do not want to design I want to use this black box. So, that means from these matrices what should I get? A directed graph. Okay. Keep all these things in mind. Okay. It is simple, but you can get trapped, you can lose track of it. So, given these two matrices, I am going to construct a graph, use this algorithm to compute the transitive closure, and somehow from the transitive closure of that graph, I am going to get my Boolean matrix product. Okay. So, here is my Boolean matrix. What am I going to do? I am going to construct a graph. The graph will have three layers. Okay. Let us have call it x, y, z. Each one will have 1 to n vertices, 3n vertices, and I am going to draw edges. The edges are going to be based on the entries in these matrices. So, whenever I have a I j is 1, I am going to make this x I j a directed edge like this. Okay. And very similarly, whenever I have b l m is 1, I am going to make the lth vertex and the mth vertex here an edge. Okay. Now, you do the transitive closure here, and the product, when is the product entry 1? So, the product A B of the product I j, when is it 1? Directed path from which I to which j, because remember there is I j, yeah, x I to z j. If there is a path, how does that path exist? Because some x I l is 1 and then x l j is 1, So, that means that entry I l must be 1 and b l j must be 1, then only we will have this path. Okay. So, that is all, right. So, given two matrices A and B where I want to compute the product, I create a 3 layered part x, y, z, draw an edge like this, then we know that there is an edge from x I, sorry, it is not y j, it is z j, x I to z j in the transitive closure, if and only if the product matrix is 1, where the product is Boolean matrix multiplication. So, what have we achieved in the whole process? Given any two matrices, I will set up this. How much time does it take for setting up this? Well, there are 3n vertices, some n square time for the edges and so on. So, there is a setup time. So, to compute the product of two Boolean matrices, I do some setting up time in n square time, and then I have a 3n vertex graph. I compute the transitive closure of it, and so B m of n is at most T c of n 3n plus order n square. Okay. So, thereby I have related that these two problems, Boolean matrix multiplication and transitive closure, have similar complexity. Okay. There was a log n factor in the other thing, but I said can be improved to, I think I will not bother. Okay, maybe I will just flash it here, that the other direction the log n can be removed by doing some extra additional work. And again divide and conquer, all that. Okay, I think I will stop here. It's already 4:45. So, what have we learned? There are some small number of problems for which we had some concrete lower bounds, that what the algorithm we have found is the best, finding max, min, max and min, even sorting, if you are happy with asymptotic complexity. Okay. In fact, it is interesting, even for sorting, the exact number of comparisons to sort n numbers is still open. I think Knuth's book has a lot of interesting challenges on it. N up to some 100, 200, it's known, but otherwise beyond that, asymptotically we know this is omega n log n, big O n log n is known, but so that's known. But then there are problems like matrix multiplication, matrix inverse, Boolean matrix multiplication, transitive closure. We have some algorithm, we don't know any improvements, and we don't have a lower bound, and that's the story for most of the problems, that we don't have a concrete lower bound, which we start looking at from tomorrow. But we have related problems in a way that you can think of them as a bunch of problems, so that any lower bound for one can immediately imply a lower bound for the other, or any algorithm for one can give an algorithm for the other. Okay. In that sense, these reductions are useful. Okay. So, we will continue this theme tomorrow. Yeah, thank you.